When designing digital circuits, we usually begin with a truth table. This is basically a table that summarizes all of the possible inputs to your circuit and their expected outputs. From here, you need a method to convert this table into meaningful Boolean expressions that you can then use to construct your circuit. This is where K-maps come into play. This will be useful when we create our adder for the 8-bit computer. K-maps can have 2, 3, or 4 variables. Let's start with a 2-variable K-map. Imagine you are given this truth table, and you are asked to draw the corresponding logic circuit. You will have to construct a K-map to obtain that circuit. The first step is to draw a 2x2 table, and then label each row and column with the variables from the truth table as shown here. A letter with a bar on top represents a 0 for that letter, while a letter without a bar is a 1. Now we are going to fill in the values of y from the truth table into the K-map, and this is done as follows. For the first row in the truth table, y is 0 when both a and b are 0. So, we go to our K-map and locate the cell corresponding to zeros for both our variables, then place the corresponding value of y in it. For the next row, y is 0 when a is 0 and b is 1. This corresponds to this cell in the K-map, so we place another 0 in there. For the third row in the truth table, y is 1 when a is 1 and b is 0, so we place the value of y in this cell, and this value is a 1. For the fourth row, y is 1 when both a and b are 1s. That's this cell in the K-map, and we place the corresponding value of y in there. Now we have our K-map filled up, and we can find the corresponding circuit. But before we do that, let us take a look at the structures for the 3 and 4 variable K-maps. The 3-variable K-map is used when we have a truth table with 3 input variables. Take note of the order in which the paired variables are arranged. The procedure for filling up this K-map is similar to that for the 2-variable K-map. For instance, if one row in the truth table is like this, then the entry cell for the output value is the one in which A is 1, B is 0, and C is 1, which is this cell. The 4-variable K-map is used when we have a truth table with 4 input variables. Again, take note of the order in which the paired variables are arranged. The procedure for filling up this K-map is similar to that for the 2 and 3-variable K-maps. Once we have our K-map for a given truth table, we want to use it to deduce the circuit that describes that truth table. Let us use this one as an example. To deduce the circuit, we need to extract what are known as fundamental products from the K-map. First, circle all groups of 1s into singlets, pairs, quads, or octets. These are the only groups that you can make, so you cannot group together 3, 5, 6, or 7 1s. Only groups of either 1, 2, 4, or 8 1s are allowed. There are some special cases at this grouping stage. First off, overlapping groups like these ones are allowed. Secondly, if you encounter a map like this one, you can roll it on itself to form a cylinder so that these edges touch. Then you can treat the grouping as a single quad instead of 2 pairs. You can also do this with 2 quads to form an octet. Lastly, you can come across a K-map like this one. The X values are called don't care values, and you can include these in your groupings to form larger groups. Larger groupings produce simpler circuits. Thus, a rule of thumb is to look for octets first in your map, then quads, then pairs, and lastly, singlets. Once you have all your groups, generate what is known as a fundamental product for each group. To do this, first look at all the rows involved in a single group and write down only the variables that are common in all those rows, meaning variables that do not change from one row to the next. If there is only one row involved in that group, write all the variables in that row, separating them with dots. Do this for all the columns involved in the group you are dealing with as well, and append the variables you get to those from the rows analysis, again separating them with dots. Repeat this for all the groups in your K-map, and then add the fundamental products up to obtain what is known as a sum of products. This is what you can now use to draw your circuit. Dots represent AND gates, plus signs represent OR gates, and bars on top of letters represent NOT gates. Going back to our original example, we can see that our fundamental product is this, meaning that Y only depends on A, and no logic gate combinations are required. Now that we are armed with this knowledge, we can use it to design our arithmetic and logic unit for the 8-bit computer. So, stay tuned for the next one.